Okay, so in today's video, we will be talking about matrices. Now, before we delve into the topic of matrices, let us first understand the definition of matrix and why we need to study matrix, what essentially helps us when we study matrices. So let's look at the definition first. The definition of matrix is a rectangular array of numbers, symbols, or expressions arranged in rows and columns. So that is the definition of matrices. So let me just underline that first for you. It needs to be arranged in rows and columns, and it's a rectangular array of numbers. So what do we mean by an array? An array is essentially a collection of numerical data or numbers or symbols or expressions as it's there given in the definition. Now, what is the practical application of matrix? So let's say we have a situation as follows. We have 4 students named A, B, C, D, and we have 5 subjects. So there's a school which teaches 5 subjects: mathematics, English, history, geography, and science. And we have 4 students. Let's say these are the 4 sections A, B, C, D, and we have chosen randomly 1 student from each of the sections. So we have 1 student from section A, 1 student from section B, 1 student from section C, and another student from section D. And we are calling the students by the name of the section that they belong to. So we are calling this student student A. We are calling this student student B. We are calling this student student C, and the final student is being called student D. So we have the numbers or the marks that they have obtained in each of these 5 examinations, and we have written them down in this table form. So this is what we all of us know, this tabular representation of data. And what we'll be doing is we'll essentially be converting this into matrix. So instead of having this list of students here and this list of subjects here, what we can do is essentially we can just let me just show you this. Let's see, there are 4 rows. So we have this first row, we have this second row, we have this third row, and we have this fourth row. On the other hand, we have 5 columns. So we have 1 column, second column, third column, fourth column, and fifth column. What I do is I eliminate this first row. This row of headings is eliminated. And at the same time, I eliminate this column, essentially the row headings. This row stands for the column headings, and this column stands for the row headings. This column essentially marks the heading of each of these rows. So what I'm doing is I am removing this row, removing this column, and I am removing this row. So what I'm left with is a set of numerical data which has 4 rows and 5 columns. That is what I'm left with. And that is exactly what I do. So I have this representation of the above same data that I have. You see 92, 92, 64, 64, 83, 83, 59, 59. So this representation is called a matrix. So let's get back to the definition. A rectangular array, that is a collection of numbers, symbols, or expressions arranged in rows and columns. So we have some rows and some columns of data. Now the definition says that it can be numbers, symbols, or expressions. So we have in our case some numbers as the data, as the concerned data that we are working with. It can, however, be symbols. We might have a situation where we don't know the mark that the student from section C obtained in history. So we might replace that with X. So that can be a particular symbol. Similarly, we might not have the marks that B obtained in geography. That can be Y. So we can replace 99 with Y. So in that case, the matrix will contain some symbols, some algebraic symbols. At the same time, we can have expressions here as well. We can be in a situation where, let's say, 78 is not known. Instead, we know of a particular expression which consists of some amount of X and Y. So that can also be an element of these matrices that we are working with. Another thing that I just mentioned is an element. So what do we mean by elements of a matrix? These singular numbers, these positions essentially are called the elements. So 92 is an element. Here 88 is an element. 64 is an element. All these numbers, all these data points that we have in this matrix are essentially the elements of the matrix. Considering the matrix that we have here, we have number of rows 4 and number of columns to be 5. So what is the significance of this? The number of rows and columns essentially give us the dimension of a matrix. So in our case, since we have 4 rows and 5 columns, we'll say that the dimension of this matrix is 4 cross 5. Please note that this is not 4 into 5. Usually the notation or the way of speaking, that is the language, is 4 cross 5. So whenever you're asked what is the dimension of a particular matrix, the dimension is essentially the number of rows cross the number of columns. So since we have 4 cross 5, we say that the dimension of this matrix is essentially 4 cross 5. Numerically, in general, we say that the dimension of a matrix is m cross n. And as I have mentioned here, this Aij represents the elements of the matrices. Now, this notation needs to be explained. So what is Aij? Here you can see that there's a subscript ij. What does that stand for? When I'm saying a particular element, the position of a particular element can be uniquely defined as the point of intersection between the considered column and the considered row. Say I want to talk about 74. So let's say that this is the element that I want to talk about. Now, how do I uniquely specify the element 74? If somebody asks me, where is the element 74? How will I tell them that this essentially is the 74 data point that I'm talking about? One easy way would be to say that I am talking about the intersection of the third row and the intersection of the third column. So here I need to know the intersection of the row and the column. The intersection of the concerned row and column will give me the data point that I am talking about. So every element will be designated or be denoted by 2 numbers. The first one will represent the row and the second one will represent the column. This ordering always needs to be mentioned, as in it needs to be remembered, because in this entire matrix algebra, we'll always be considering the rows before the columns. So we'll always move in this direction first. So let me just put a different color over here. So we'll always move in this direction first, and then we'll move in, let me just put a straight line, and then this is still not a straight line. And then we'll essentially move in this direction. So we'll first consider rows and then we'll consider columns. This order needs to be maintained always. So let's go back to the element that we were talking about. So let's say I want to talk about 74. How will I represent that? I'll say this is the element which corresponds to the third row and the third column. So that is 74. That is how I represent each element of the concerned matrix. Now try this out for yourself. If there are 4 rows and 5 columns in a row, then how many elements are there in a matrix? So of course, what you can do is you can count the matrices. You can draw out the matrix. Since there are 4 rows and 5 columns, it will imply that I'll have this format. The numerical data of the points need not be considered. We know that we'll essentially be having 4 into 5 data points. That is essentially 20 data points. Now, again, as you can see here, we have some notations involved here. So what we do is this I number, that is the number of rows, essentially runs from 1 to m. So you see, as I mentioned before, m is the number of rows and n is the number of columns. So as I mentioned, 4 is the number of rows, 5 is the number of columns. So I, which denotes the row number corresponding to that particular element, will run from 1 to m, and j, which denotes the particular column of the element concerned, will run from 1 to n, because this represents the column. So let me just write it down. This represents the row. So the first number will represent the row and the second number will represent the column. That is the basic notation of matrix algebra. Now we'll move on to look at some types of matrices. So this is just a basic introduction, so we'll not move into the details. Of course, as we look into the nitty-gritties of matrices, we'll further develop some more types of matrices, and so we'll be continuously moving back and forth into the definitions, examples, and working out of certain sums and certain theories and properties, etc. But as we move on, we'll be adding to the knowledge that we have accumulated so far. So let's look at some types of matrices that we can analyze given the knowledge that we have until now. So the first matrix that we'll be talking about is a rectangular matrix. Now, as I had defined before, a matrix is a rectangular array of numbers. So a rectangle can essentially be defined in two ways. One is a strict way where we say consider the geometry. If you're given a diagram like this, you can close your eyes and not exactly close your eyes, you'll have to see, but you can be very confident and say that this is a rectangle. But what happens if you're given a diagram like this? This doesn't look what I want it to look like, but assume that these are straight lines and assume that all the straight lines have equal length. So if you are asked, is this a rectangle or a square, then what will you answer? In strict sense, you will be saying this is not a rectangle but a square because it has four sides of equal length. However, in certain cases or in certain theories, we say that a square is a form of a rectangle. A rectangle essentially has properties such as it has four sides, which are all four of them are perpendicular to each other. So essentially there are two ways. In a stricter sense, this is a square and not a rectangle, but in a broader sense, this is a rectangle and at the same time it is a square because it has an added property. Besides being a rectangle, it has an added property that the four sides are of equal length, and so hence it's a square. So when we are defining matrix, we are looking at the more lucid, more broad-minded and more open definition where we are considering both the fact that the number of rows and the columns can be equal. So essentially, if we look at it geometrically, this rectangular consists of these both cases. So we are considering of rectangles as well as squares. However, when we are talking about rectangular matrix and square matrix in the types of matrix, we are looking at the stricter versions or the stricter definitions. So a rectangular matrix is essentially a matrix where the number of rows does not equal to the number of columns. So look at our example. We have 4 rows and we have 5 columns. So the number of rows and number of columns do not match with each other. They are not equal to each other, and hence we can say that the example that we have considered here is a rectangular matrix. Square matrix, on the other hand, has equal number of rows and columns. So the value of m and n. So m represents the number of rows and n represents the number of columns. We'll have m equals n for square matrices. So what happens if, let's say, if I remove this column, that was a very aggressive line, but let me just remove this column. That will give me 4 rows and 4 columns. I have removed the 5th column and hence I'm left with only 4 columns. This matrix, let me just mark it with a different color then and a different symbol. So this matrix will essentially be a square matrix since it has 4 rows and 4 columns. So hence we know what is a rectangular matrix and what is a square matrix. The next thing that we come across is row matrices and column matrices. Now, row matrix is essentially a matrix where for row matrix, the number of row is 1. So now let's look at the data that we have here. Consider a situation where we have just this data point or this data set. So we have only taken the first 4 elements of the first row. Or in fact, you can actually involve this as well. So let me just, let me remove these. Yeah. So let's consider this matrix. Of course, you will say, why is it a matrix? This is not a rectangle. This is not a data set. Yes, this is a matrix. As I mentioned, matrix is just a rectangular array of numbers. There is no restriction to the number of rows and columns that it might have. It might have 1. Essentially, it needs to have at least 1 row and at least 1 column. In that sense, a singular data point is also a matrix because it has 1 row and 1 column. That gives us a single digit, a single unit data point. But in our case, let's see, we have one row and we have 5 columns. So this is essentially a row matrix. So let's see, row matrix, it has m equal to 1. If we look here, the value of m will be 1 and the value of n will be 5. So this is 1 cross 5 matrix, as in the dimension is 1 cross 5. So this is a row matrix. Now, if that is a row matrix, then what is a column matrix? Let's look at another example. Let's say I take this and this. So just a second, this and this. So we have 78, 26, 74 and 70 as the matrix concern. This, on the other hand, will be a column matrix because it has 1 column and it has 4 rows. So the dimensions of these matrix will be 4 cross 1. So now we know what is a row matrix and a column matrix. Essentially, a row matrix has only 1 row, hence the name, and a column matrix has only 1 column, hence the name. Do note that row matrices and column matrices are also called vectors. So if you're talking about row matrices, you might also be talking about row vectors. They are called vectors because they have only 1 row or only 1 column. You have to have at least one of the rows and columns to be 1 in number. So if a particular matrix has 1 row or a particular matrix has 1 column, it is said that the matrix is a vector. So it can be a row vector or a column vector. If it's a row vector, it has 1 row, and if it is a column vector, it has 1 column. So we'll keep it till this much. In the next video, we'll start from the 4th point, where we'll be discussing null matrices, diagonal matrices, scalar matrices, unit or identity matrices, and so on.